Hello friends, welcome to our new episode. In this episode, we are going to discuss phase rule. Actually, this phase rule is a rule which concerns heterogeneous equilibria. So, we are dealing with systems in which we have more than one phase and they are in equilibrium with each other. These phases are in equilibrium. So, such systems are considered and how the principles of thermodynamics is applicable here and how we get useful rules and how it can be applied to concrete situations. That's we are going to see in this episode. So the phase rule, the rule can be stated by one equation, F equals C minus P plus 2, where F stands for degree of freedom. So we are going to see, these are the number of independent variables. C is number of components in the system, chemical species. There are also some qualification we have to apply, later we will see. P is of course the number of phases present in a system in equilibrium, plus 2. Right, that holds good for any heterogeneous equilibrium. That is it. Now we can see the different aspects of phase rule. So we can see that this phase rule is strictly applicable, certain condition, if it is to be applicable, certain conditions should be satisfied. Equilibrium between any number of phases. And it should not be influenced by gravity, electric or magnetic forces or by surface action, but influenced by temperature, pressure and composition or concentration only. Then this rule, that is the degree of freedom, number of components and number of phases are related by an equation, by this expression F is equal to C minus P plus 2. That is it. So certain conditions apply there. Okay, we should be aware of that, aware of these conditions. That's all. Okay, now we can define the terms. We can examine what are these terms involved here. Phase. It is defined as homogeneous, physically distinct, mechanically separable portion of a system. Suppose we have ice and water. Ice is a solid phase, separate from water phase, the liquid phase, and there is a surface or a boundary between the solid and liquid phase. Similarly, we can have vapor phase and liquid phase. So there is a boundary separating them, right? So it should be physically distinct, and we are going to see that all gases will form a single phase only. Gases are completely miscible, but in the case of liquids, you can have miscible liquids where we have one phase only. If you take alcohol water system, they are miscible in all ratios, then we will get a one phase. We have one liquid phase only, right? Then we can have completely immiscible liquids like benzene and water. They will form two different phases. Or phenol and water, they are partially miscible. Then also you will get two phases. That will be a saturated solution of water in phenol and phenol in water, right? All solids form different phases usually, except for solid solutions that we will later come across. Otherwise, solids form different phases. That is it. Okay, now we can come to component. Component is the chemical species we know. It is defined as the smallest number of independently variable constituents by means of which the composition of each phase can be expressed in the form of a chemical equation. That is it. Suppose we have a system involving a chemical equilibrium like calcium carbonate in a closed vessel. We heat it, temperature is kept constant, then an equilibrium will be established as calcium carbonate decomposes to calcium oxide and carbon dioxide. Once equilibrium is established, the pressure of carbon dioxide will remain as such. That we know. Now, we can have three phases there. One is calcium carbonate solid phase, calcium oxide solid phase, and carbon dioxide gaseous phase, right? And the chemical composition of any one of the phase, solid phase or the gaseous phase, can be expressed by means of what we call two chemical components. You can choose any two among the three chemical species there, calcium carbonate and calcium oxide. Suppose we choose. So calcium carbonate phase is calcium carbonate plus 0 calcium oxide. Right? The composition and number of calcium carbonate plus 0 calcium oxide. In that way we can express. Or if it is calcium oxide, obviously it also can be expressed. If it is carbon dioxide, we can express the chemical composition as CaCO3 minus CaO. That will give you carbon dioxide. So it is the minimum number of chemical species we require, and using which we can express the composition of any one of the phase, right? By using chemical equations. That's all. So ammonium chloride decomposes to ammonia and HCl. There also we require only two components, not three components. We have three chemical species, but number of components will be taken as two. That is the significance of this. Right. Now we can consider a concentrated solution of ammonium chloride in water. Sorry, a saturated solution of ammonium chloride in water. Then there can have number of different phases. Ammonium chloride, a solid phase. Then solution of ammonium chloride in water, that is a single phase, liquid phase. Then of course you will have gaseous phase also. Right. Degree of freedom is defined the minimum number of independent variable factors such as temperature, pressure and concentration. We consider intensive variables here, right? Not extensive. Intensive variables such as temperature, pressure and concentration of the phases or composition of the phases, which must be fixed in order to define the condition of the system completely. To define the system completely, we want to define the temperature. We want to know the temperature, pressure, and of course the composition of each phase. So we require a number of concentration terms. If different components are present, we want to know the concentration of these components. And all such variables taken together is what we call degree of freedom. Okay. Now we can come to what you call the phase rule, how it can be obtained from principles of thermodynamics. Consider X as the mole fraction of any component. C, in a phase P, we put it as XCP. C stands for the component, a particular component, and P stands for the phase in which it is present. Right? We have a solid, liquid and gaseous phase in an equilibrium system. Then X solid, X of a particular component in solid phase, we can say. X of that component in liquid phase, X of that component in gaseous phase, and so on. Right? In that way, we can take different components. So the composition can be given like that. For phase 1, first phase, we can have a number of phases. P phases are present there, suppose. So we put X11, X21, X31, and so on. X11 stands for the first component, first phase. X21 stands for the second component, first phase, and so on. Then X12, 22, and so on. That for the phase 2, then for phase 3 up to phase P. Right. The total number of such variables will be, so we require mole fraction of how many components? C minus 1 components in a particular phase. Why? The last component, the Cth component, the composition get fixed if you know the composition of all other components in a particular phase. So we require the composition of C minus 1 components only. So the total number of composition variables will be P into C minus 1. Plus, we have to fix the pressure and temperature also if the system is at equilibrium. So we have to know that also. So the total number of variables is P into C minus 1 plus 2. P into C minus 1 is the composition variables and 2 is the temperature and pressure variables. Now, if a system is in equilibrium, there are constraints. That is from thermodynamics. the chemical potential of a component in all of these phases should be the same. That is the thermodynamic constraint. Then only these phases can be in equilibrium. Chemical potential stands for what we call partial molal free energy. That's nothing but free energy per mole of the component in that particular phase. And for a component, its chemical potential in different phases which are in equilibrium with each other should be the same. So we are applying that constraint. So you can have P minus 1 relations for each component. And when you fix when we have the same chemical potential, what happens? Some of the variables also get fixed, right? So we are applying these constraints. We can, certain variables get fixed automatically. P minus 1 variables will get fixed automatically by means of this constraint, equilibrium constraint, that comes from thermodynamics. Okay. Now, total number of constraints will be C into P minus 1. Okay. P minus 1 constraint for particular component. So, number of components is C. Now, degree of freedom will be variables minus constraints. That is. So, P into C minus 1 plus 2 minus C into P minus 1. So, F is equal to C minus P plus 2. So, this is a heuristic derivation of what we call phase rule. That will do for your board exams or university exams. So, this rule holds good for any heterogeneous equilibrium. That is the significance of this. Okay. Phase equilibrium is a common assumption used in process of systems modeling. It relates the equivalence of temperature, pressure, and Gibbs free energy of a species in the phase considered to be in equilibrium. If a system is in equilibrium, it is having a number of different phases. What should be there? The temperature, pressure of all the phases should be equal. They should be the same. Then only they can be in equilibrium. That is it. Then one more thing has to be in equilibrium. The Gibbs free energy per mole of the components also should be the same. Why? At equilibrium, one component can get converted reversibly into a component in a particular phase can be converted into the other phase reversibly if the system is at equilibrium. So, suppose we have component 1, it is converted from phase 1 to phase 2. Suppose we have ice and water at equilibrium at 0 degrees Celsius, 1 atmosphere pressure. You can reversibly convert ice into water. Okay? And if it is a reversible conversion, ice and water are at equilibrium at that particular temperature and pressure, then what does it indicate? For reversible conversion, there should not be any change in free energy. Delta G should be 0. That means free energy of ice and water should be the same at that particular temperature and pressure. That's it. So, chemical potential is nothing but free energy per mole. So, it should be the same. The chemical potential of a component in all the phases should be the same if equilibrium is kept. So, that we get from thermodynamics. That is applied here, then we get the phase rule. That is it. So, this is the thermodynamic condition for or criteria for phase equilibrium. Temperature should be the same in all phases. Pressure should be the same in all the phases. Then GI bar. What is GI bar indicates? GI bar simply indicates chemical potential or free energy per mole. That's it. Hope you get it. Okay, that's fine. Now we can apply this phase rule to different systems. One component systems we can take. The equation is the same. F is equal to C minus P plus 2. We can know what is the maximum number of phases that can coexist in a one component system. In a one component system, what happens? number of components is put as 1, then suppose degree of freedom, I put it as 0. So we are considering an invariant system, right? So that we can know it is an invariant system. Degree of freedom we have minimized. Degree of freedom, that it is 0, that means everything is fixed. Then we can see that P is equal to 3. If you solve this expression, we get P equals 3. What does it indicate? In a one component system, the maximum number of phases that can coexist is equal to 3. That is it. So you take a one component system like water system. So in water system, only 3 phases can coexist: ice, water and water vapor at a particular temperature and pressure. Only at that particular temperature and pressure these phases can coexist. That is the maximum number of phases that can coexist, right? Similarly, we can consider the maximum degree of freedom such one component system can have. How we can evaluate that? We consider the number of phases to be minimum. When the number of phases can be minimum, when there is only one phase, it is liquid phase or gaseous phase, whatever it may be. Component is also equal to 1. Then what you get? Degree of freedom is 2. 1 minus 1 plus 2. So in a one component system, maximum degree of freedom is equal to 2. That is, we can know from this expression. Maximum number of phases that can coexist is 3, and maximum degree of freedom it can have is 2. One component system. That is the case of one component system. Okay. The most convenient example of one component system is our water system. The simplest system we take into consideration is water system. And we have phase diagram here. Phase diagram, in this case, we can take it as a pressure temperature. Because here we know composition, we have only one component. Composition is 100. Or composition is 1 everywhere. Mole fraction is 1 everywhere. Only one component. So the two variables are pressure, temperature variables. Here you can see certain lines or curves as well as certain points and certain areas. So areas represent what you call bivariant system. Areas consist of a single phase only. Right? So this area correspond to what we call gaseous phase. Okay? That is temperature and low pressure. Under that temperature and pressure range, the area AOB here is what you call water vapor alone. So there it is bivariant. System will be bivariant. Both temperature and pressure can vary. Similarly, the area AOC, that consists of, under that pressure and temperature range, we will have liquid water. That is it. And there also the system is bivariant. And what about COB? The area included between these two curves, that will be our solid phase. That consists of ice alone. There also the system is bivariant. And we have this curve OA. That is called the vapor pressure curve of liquid water. It gives us the variation of vapor pressure with temperature. Or we can consider it as the variation of boiling point of the liquid with confining pressure. Both is given by the same curve. OA curve gives. Can be considered as how the vapor pressure of the liquid water changes when you change temperature. Or we can consider as the variation of boiling point of water when we change the confining pressure. Right? That is governed by that variation is governed by a thermodynamic expression called Cauchy-Clapeyron equation. Later we will see. Now we leave it as such. So OA, along OA, we have two phases in equilibrium. So along OA, the system will be univariant only. Two phases are there. Then if you put in the equation F equals C minus P plus 2, P is put as 2, then you get degree of freedom as 1. So what does it indicate? If you change pressure, temperature changes. That is, if you change confining pressure, boiling point changes. Or if you change temperature, vapor pressure changes. That is it. New equilibrium will be established. That is it. Okay. Similarly, what is the curve OB represent? It is the sublimation curve of ice. So where we have solid ice in equilibrium with vapor, water vapor. Ice under low temperature, below the melting point, can vaporize directly to some extent, even though the vapor pressure will be low. There will be small vapor pressure for solid ice also. So that is represented. We say sublimation curve. So how the sublimation temperature changes with confining pressure, we can consider it like that. Right? Okay. Then OC, that is what we call the melting point or fusion curve of ice. Fusion curve of ice. Along which we have liquid and ice, solid and liquid in equilibrium with each other. That also a univariate system. So it gives the variation of melting point of ice with pressure. You can see the curve has a negative slope here. What does it indicate? It slants back. What will be its indication? When you increase pressure, melting point decreases. Usually the case is different for solids. For water it is the reverse because of anomalous expansion of water. Right, whatever may be the reason. So if you put the phase diagram for water, you should be very particular that OC curve, the melting point curve of ice slants backwards. Ensure that in your university examination. Otherwise, the diagram will be considered as false or wrong representation. OC curve should slant back. That you should be very particular. Now you come to the point O. That is what we call triple point. At that point, we can have ice, water, and vapor can be in equilibrium with each other. And you can see that three phases are there, then degree of freedom will be 0. What does it indicate? Only at a particular temperature and pressure. That is 4.58 millimeter of mercury pressure and 0.0075 degrees Celsius. All the three phases can coexist. Only under that condition. That is it. Then we have a small dotted line curve here. What is that? Dotted line curve, OA prime. OA prime is what we call the metastable equilibrium, where your liquid water is in equilibrium with vapor itself, but you have supercooled water. That is metastable. So if you carefully cool water below 0 degrees Celsius, what can happen? It may not be converted into ice. It remains as in the liquid phase. And if you apply some disturbance, it will go into, or if you give seedling by putting a small piece of ice, then also it can go to the solid phase. Otherwise, we can have supercooled liquid in equilibrium with water vapor. That is represented by the OA prime. Okay, that is it. That is the water system. Then we can have what you call the sulfur system. Sulfur has two different solid forms, monoclinic and rhombic forms, right? And it can have liquid phase and it can have solid phase. Sorry, it can have vapor phase. But this is a one component system. Only three phases can coexist in such a system. Maximum number of phases that can coexist is three. So all the four phases cannot be in equilibrium with each other in sulfur system. So the areas has the same significance. Here you have sulfur vapor under such pressure and temperature condition. Here it is liquid sulfur. This is rhombic sulfur, and the area inside this approximate triangle is what you call monoclinic sulfur. The curve CD. In the area, the system is bivariant, as we have seen. CD. What the curve CD indicates, that is the vapor pressure curve of liquid sulfur. That's all. Or boiling point curve of liquid sulfur. How boiling point varies with confining pressure, or how vapor pressure varies with temperature. Quite as simple. And what is this curve VA? Here we have what we call the sublimation curve for rhombic sulfur. Under such pressure and temperature condition, what can happen? Solid rhombic sulfur can converted into vapor phase. They are in equilibrium. There it will be univariant. System will be univariant. That we know. Then what is this curve BG indicates? Sorry, EG indicates. EG is the melting point curve of what we call solid rhombic sulfur. How the melting point varies with pressure, confining pressure. Melting point varies with pressure. That is given by the expression. You can see that the curve is slanting forward. That you should be very particular. Why it is slanting forward? The melting point increases with increase in pressure here. In water, it bend backwards because the melting point decreases with increasing pressure. That we should be very clear. Okay. Then we have this point E. Here you can see that that is the what we call the temperature at which before that you have to consider BE, the curve BE also. What is that indicates? That is also an equilibrium. Equilibrium between two solid phases. How metamorphosis, this conversion of solid rhombic sulfur into monoclinic sulfur can happen. It can happen by annealing. It can happen by at particular temperature and pressure, and they can be in equilibrium under these temperature and pressure conditions. And transformation curve of rhombic sulfur into monoclinic sulfur is indicated by this. So beyond the point E, monoclinic cannot exist. So at E, we can have a triple point. It is a triple point where we have two solid phases. Monoclinic and rhombic is in equilibrium with the liquid. Okay, that is an invariant point. Similarly, Z, this is another invariant point, C. Here we have liquid, gas and monoclinic in equilibrium with each other. Then we can be another invariant point or a triple point where rhombic, vapor and monoclinic, two solid and vapor phase are in equilibrium with each other. Then you can see, it is not very clear, dotted line extending from B to F here. Similarly, a dotted line extending from C to F here and E to F here. So if you do not do the heating or cooling very slowly, the formation of monoclinic crystals will not happen. Liquid sulfur you are cooling. If cooling is done not very carefully, conversion into monoclinic sulfur will not separate out even at E. What will happen? Rhombic sulfur will separate out. And we have this rhombic liquid equilibrium along EF, and along that is metastable. CF we have again liquid gaseous metastable equilibrium. Along BF we have metastable equilibrium of rhombic and vapor. That is it. Right? We can have such metastable equilibrium. F is another triple point, metastable triple point, where we have liquid, rhombic and gaseous phase. Liquid, rhombic and gaseous phase. Normally there is no point where these three phases can in equilibrium. That will be a metastable equilibrium only. That is sulfur system. Okay, now we have to move on to what we call two component systems. What is the peculiarity of two component systems? We put number of components as 2 and we can write degree of freedom as 4 minus p, and number of phases, if you put number of phases as 1, then the maximum degree of freedom will be 3, right? So we will have to know temperature, pressure and composition of one of the variables at least. Then only we can know define the system completely in this case, right? So 3 variables we have to have the variables. Which variables? Temperature, pressure and composition. And usually we represent the phase diagram in 2-dimensional figures, and to represent 3 variables 2-dimensional figure is not easy. That can be done in a particular manner, in a triangular picture representation is done sometimes, but that is a difficult thing. Or you should have a 3-dimensional model for it, right? But there is some convenience. The convenience is that we can have systems where this, in which only solid and liquid phases are considered. We ignore the gaseous phase. And suppose we have the systems at 1 atmosphere pressure, under atmospheric pressure itself, and the pressure variable does not have much effect on this solid and liquid, and we can ignore that pressure variable. Condensed system we call, and the degree of freedom of the system by 1, this reduces, right? We call it as condensed phase. The vapor phase is ignored here, right? So the phase rule equation is rearranged as or reformed as F is equal to C minus P plus 1. That is for our convenience. The strict phase rule should be the other thing itself, but we can put it as, because we are ignoring the gaseous phase. Okay. So we are considering solids and liquids alone, and among the solids and liquids phases we can have different type of 2 component systems. We can have different what we call eutectic systems, simple eutectic systems. Then we can have where the components react. Simple eutectic system means the components do not react and they are completely miscible in liquid state, but immiscible in the solid state. That is our eutectic system. So eutectic system consists of 2 substances, say A and B, and A and B are completely miscible in the liquid system, but in the solid system they are completely immiscible. That is the definition for a simple eutectic system, and they do not react chemically. Now compound should be formed between the components, like our salt and water, right? We can mix it together. In liquid system they are almost completely miscible at all ranges, but solid they will be forming separate phases. Okay, a simple eutectic system can be represented like this. Here the variables are temperature and composition. Okay, the pressure variable is ignored because we are ignoring the vapor phase, and the curve somewhat look like this. So the point A represents the melting point of pure A. The point B represents the melting point of pure B. The curve AC is called the melting point curve of solid A. The melting point changes. When it changes when you add the other component. So, when you change the composition, the melting point changes. So, if you add salt to ice, it will start melting. It will melt at temperatures below the normal melting point of water. That is it. So, B is added to A, the melting point of A will decrease along this point. Similarly, A is added to B, its melting point decreases along this point. And they meet at a particular point. And there we have this liquid phase, solid A as well as solid B. And that mixture is what we call eutectic mixture. And the eutectic mixture has the lowest melting point. And along the curve AC, we can consider that solid A is in equilibrium with solution. Along the curve BC, solid B is in equilibrium with solution. And at C, so if you apply the reduced phase rule, this is univariate. The curve is univariate, AC as well as BC. C will be where we have the liquid phase, solid A and solid B, that is the eutectic mixture. They are in equilibrium with each other. We consider it as an invariant point, that is a triple point. We can consider it as an invariant point. Okay. Below this horizontal, we will have solid phase only. So here we have solid A plus eutectic. Here we have eutectic at this point. Here we have solid B plus eutectic. That is solid A plus solid B, that ratio. Okay, that is it. This is a simple eutectic system. Now, suppose we have a liquid corresponding to the composition alpha. If you cool it, the liquid phase will come down. At the point beta, what will happen? Beta solidification will start. And now the composition of liquid phase will vary. Solid phase, A will separate out. At the point beta, A will separate out. Then what will happen? The composition of the liquid phase will vary along beta C. Once C is reached, what will happen? B also will start solidifying, or the eutectic mixture will solidify there. Okay. Suppose we have a liquid of composition gamma, that is eutectic mixture. You cool it up to the point C, it will remain in the liquid state, and at the point C, both the solids, the eutectic mixture will precipitate out, solidify. Now we have a liquid of composition alpha 1 at that particular temperature, and if you cool it, it will cool along alpha prime to beta prime. It will remain in the liquid phase itself. At beta prime, what will happen? The solid B will start separating out. And what happens to the liquid phase composition? It will vary along beta C. And at C, both A and B will separate out. That is it. That's how the eutectics behave. Lead silver system, lead antimony system, zinc cadmium system, potassium iodide water system, etc. are examples. Okay, this is a lead silver system. The points explained for A and B is true here also. This is 100% lead, its melting point 600 Kelvin, silver 1234 Kelvin. Right, the eutectic mixture consists of 2.6% of silver. Okay, and this phase equilibria is utilized in the separation of silver from, in small amount, silver will be present in lead obtained from the ores of lead. We want to separate that silver out because silver is a costlier metal. We can separate it out. It contains in traces in your lead. So what you do, you liquefy the impure or what you call argentiferous lead, which contains small amount of silver. Okay, then you cool, slowly cool it. It comes X to Y, it comes. At Y what happens? Which will start solidify, lead will start solidify. And the composition of the liquid phase, you can separate out that lead. Okay, you go on doing that. Lead is separated out. And the composition varies of the liquid phase varies along YC. At C what happens? Both silver and lead crystallize out together. They solidify together. And you get solid which contain lead contain 2.6% of silver. The concentration of silver you can increase up to 2.6% by simply melting and cooling. That is it. Now you can utilize chemical methods to separate silver from it. Usually lead is easily oxidized and blown off. Silver is not that easily oxidized, and we can, in that way, we can separate silver from that. Pattinson process it is known as. Okay. So initially to increase concentration from small traces, it may be 0.001 or 0.1, 0.01 etc. percentage. That you can increase up to 2.6% by simply melting lead and cooling it slowly. When you cool it slowly, lead crystallizes out and lead is removed, continuously removed. Okay, that is it. Okay, now we can have other type of systems. You have two components A and B, they react to form a compound, suppose. And there can be two types of such systems where you have congruent melting point. Congruent melting point simply means that the compound can melt without change in composition. That is it. The compound is not decomposed during melting. That is it. Incongruent melting point, what does it indicate? The compound decomposes when converted into liquid phase. In the liquid phase, the compound do not exist. Only in the solid phase, the compound exists. In the case of congruent melting point. Sorry, incongruent melting point. Congruent melting point, the compound can exist both in solid and liquid phase. It is stable in solid and liquid phase. So it can melt without changing composition. Incongruent melting point, what does it indicate? It melts with changing composition. In liquid phase, it is not stable under given pressure condition. If we change the pressure condition, sometimes it can exist even in liquid phase, even in incongruent melting compound. That is another thing. But here we are considering condition of atmospheric pressure only. Then we have what we call formation of solid solution. That so far we have considered that solids form separate phases. If the solids form what we call solid solution, completely miscible. In some cases, the what we call the lattice particles of one substance can be replaced by that of other substance. We can have what we call solid solution. That is another thing. Okay. A compound AB is formed. Suppose we get a compound AB equal molar ratio. 1:1 ratio, they can react to give you a compound AB. Then the diagram, phase diagram, somewhat look like this. It can be considered as a combined phase diagram of A and AB and B and AB. Right, up to this. Then it will be very simple to see. This is the phase diagram for two substances, two components. You consider for convenience only. Actually, there are not three components. We have only number of components is defined as two only. But you consider the species like this. AB is one species, A is another species. It has one phase diagram. Then AB species and B species, we have another phase diagram. Then things are quite simple. That's why I have D is the what we call the congruent melting point of our compound AB. Okay. Solid A is melting point curve of A. Along this AC, solid A is in equilibrium with the liquid melt. D is the melting point of pure AB, and along DEC, compound AB is in equilibrium with the liquid phase. Okay, and B is the melting point curve of B. Here along B, solid B is in equilibrium with the liquid phase. Okay, right. Now if you consider this area, solid, here you will have solid A plus liquid. If you want to know the composition of the liquid phase, you can simply draw a horizontal. When the horizontal meet the graph, you will have the liquid phase composition. Solid phase will be solid A itself. That is it. Because if you cool a liquid here, what happens? Its composition of liquid phase will change along this point. So if you cool to, say, the point at which this cursor is present, the total composition will correspond to that cursor point itself, but liquid phase composition will be that a horizontal line. You draw a horizontal line here. That is it. Okay. DC curve, I have explained it. And you have this horizontal. What does it indicate? Two different composition can have the same melting point. That is indicated by X and X on. Two different compositions of the same melting point. That is indicated. So DC you can consider as the melting point of pure AB decreases with when you add A to it. You can consider it like that also. So in this area we have compound AB in equilibrium with the liquid phase. Okay, that is it. Beyond these two horizontals, you will have solid phases alone. That silver is simple euteric. Okay, fine. This is magnesium zinc system. That is an example of a compound of a system in which we have a congruent melting compound. MgZn2 is formed. Right? Magnesium, here we have zinc, 100% zinc. Right? This corresponds to MgZn2 formula. So C and E are euteric points. At the point C, we have two solids, zinc and this compound, magnesium and zinc compound, MgZn2. That is a compound of magnesium and zinc. Okay, that is a euteric mixture plus the liquid. Similarly, E, what does it indicate? We have euteric of magnesium and the compound here, and it is in equilibrium with the liquid. D is the congruent melting point of our compound. That is it. Now we can have the other type of system, what you call incongruent melting point. So we have a compound here also, but the compound does not melt without change in composition. What happens to its is that its composition is changed when it melts. Okay, that is it. So AC as the usual significance, you have the solid AB2 plus solid A here, and DC is the what you call the melting point curve of the solid AB2, and BD is the melting point curve of what we call the solid B. So here we have liquid plus solid B. Beyond the horizontal we have solid B and solid AB here. Here we have solid A plus liquid. Below this horizontal we have solid A plus solid AB2. Here we will have what you call solid B plus solid AB2. Okay, C is a eutectic point and D is what you call the incongruent melting point. Okay, what happens to solid B at this point? It melts into the liquid solution. Liquid solution, there is no solid AB. There is no solid AB2 in the liquid solution. We have a mixture of A and B only in the liquid solution. That is, AB2 do not exist in the liquid state, right? So at D, at the point D, the melting point, you have the liquid solution that is in equilibrium with the solid AB2 as well as solid B. That is it. Okay, that's right. D prime here is what we call the metastable equilibrium, where we have the what we call the theoretical melting point of our compound. We can reach if it does not decompose. D prime will represent what we call theoretical melting point. We can actually, in most of the incongruent melting compounds, we can have it melted without change in composition when you increase pressure. That is another thing. Okay, that's fine. That will do for the time being. So we have gone through a number of systems and its significances we have considered, and you have what you call potassium iodide water system, and of course sodium sulfate water system, etc. are there. That examples you can simply go through. Potassium iodide water system is simple eutectic system, and sodium sulfate water system is what you call incongruent melting system. Compound is formed. A number of compounds are formed between sodium sulfate and water. Decahydrate, heptahydrate, and anhydrous sodium sulfate are there. They are considered as compounds of sodium sulfate and water, which can exist in the solid phase only. That's it. Okay. The phase diagrams are not shown here, but you can examine your textbook and get the significance. You can get along the explanation very easily. So this is an introduction to phase rule. Now we can go into what we call the questions discussion of phase rule, that in another session. Thank you.